In this video, we prove the information matrix equality, which states that if our model is correctly specified, in other words, f evaluated at the pseudo-true parameter theta naught, is equal to the true data generating process p naught, then the matrices K and J, defined as follows, coincide. We begin by deriving a simpler expression for K. The variance of a random vector x is equal to the expectation of x multiplied by its transpose minus the expectation of x multiplied by the transpose of the expectation of x. Applying this to the quantity d theta log f, we obtain the following expression. Now take a closer look at this component. We know that theta naught, the pseudo-true parameter value, maximizes the expected log likelihood. So assuming that we can interchange derivative and expectation, which under certain regularity conditions we can, this tells us that the expectation of d theta log f is equal to d theta times the expectation of log f is equal to 0. That's because this is the first order condition for a maximum. In other words, K is equal to the expectation of this outer product, and we don't have to worry about the remaining terms. So, to show that J is equal to K, it suffices to establish this simpler equality. The rest of the proof is devoted to establishing the claim inside this box. To prove it, we will proceed element by element and examine a representative element of this matrix on the left-hand side compared to this matrix on the right-hand side. Consider an arbitrary element, I, j, of the second derivative matrix. This is the derivative with respect to theta I of the derivative with respect to theta j of the log of f. First, we'll calculate the inner derivative. The derivative of the log of f is 1 over f. And then, by the chain rule, we have to take the derivative of f with respect to theta j. Now we have two functions. We can think of this one as a, and we can think of this one as b. And we need to calculate the derivative of the product of these functions with respect to theta I. We'll do this using the product rule. First, we have dA d theta I times b. Then we add to this a times dB d theta I. The remaining two equalities on this slide factorize the first term in the product rule in a slightly different way. Notice that if we split up the 1 over f squared, so we associate 1 with the derivative with respect to theta I of f, and another with the derivative with respect to theta j of f, we have two rather familiar looking terms. These are in fact equal to the derivative of the log of f with respect to theta I and with respect to theta j, respectively, giving us the following expression. We obtained the following expression on the previous slide. If we multiply this by -1 and take expectations, then we obtain the following. The expectation of the derivative with respect to theta I of log of f times the derivative with respect to theta j of log of f minus this term. Notice that the first piece is precisely our alternative expression for k. So it suffices to show that the second piece is equal to 0. On this slide, we complete the proof by showing that the expectation in the box is equal to 0, which, as argued a moment ago, is sufficient for establishing that k is equal to j. And here is where we will use the assumption that the model is correctly specified. Let's write the expectation of interest as an integral. It is the integral of this function multiplied by the true distribution of y, which is p naught. But if p naught is in fact equal to f, then we obtain a very helpful cancellation. This f in the denominator cancels with this f in the numerator. This leaves us with the integral of the second derivative of the density with respect to theta I and then theta j. If we can interchange derivative and integral, which under certain assumptions we can do, then we can write this as the second derivative of the integral of the density with respect to y. But because f is a density, this integral is equal to 1. And any derivative that you care to take of 1 is equal to 0. Thus, we have shown that the expectation in the box is 0, which, as argued before, is sufficient to show that an arbitrary element of k is equal to an arbitrary element of j. Since all of the matched elements of these two matrices agree, the matrices themselves agree, and we have proved the information matrix equality.